Okay, so last part of chapter or lesson 29. So we're going to relate free energy to equilibrium. So there is an appendix in the back of the book that's going to have a bunch of values, and these values, these G values, assume that the reaction has reached equilibrium, or Q equals K. However, when the reaction occurs at other conditions, we have to use this equation, okay, which has the delta G that's not at equilibrium, the delta G that is at equilibrium, the not, R times T, and then Q, which is the reaction quotient. Okay, R is going to be our ideal gas, the 8.3145. And T are going to be our temperatures in Kelvin. Okay. All right, so let's practice some questions. The first one says to calculate the Q and the delta G reaction for the following. Okay. And then determine how the conditions compare to equilibrium conditions in the table below. So my first thing is that Q is still going to be products over reactants. Water isn't going to appear in my expression because water is going to be equated to 1. I'm going to square because of the 2 in ammonia and multiply that by the pressure of CO2. And so now I'm going to plug all of my values in. Multiply the top and the bottom, and I see that Q is equal to 0.001. And if I go down to the bottom, I see that when K is less than 1, we see that the reactants, that there are more, well, we're not going to compare it yet. When Q is this value, it means that there are very few products. Mainly reactants at this point. Okay. So let's look at delta G. Now, with the delta G values, you need to look them up in the table, and I've looked up those in the back of the book. And we're going to add the products and then add up the reactants, making sure to multiply ammonia's value by 2. And the value that you should get is negative 13.6 kilojoule. When we have a negative G value, this tells us that the products are favored over the reactants at equilibrium. So we're going to predict that the reaction will shift right because Q indicates there are very few products. So what this means is the reaction is going to shift right to produce the products to put us at equilibrium. Okay? So let's look at Q in the next one. Now it's going to be 1 divided by 0.1 times 0.1, and Q is going to be equal to 1,000. This tells us lots of products, very little reactant. The delta G is still going to be negative 13.6, which would indicate that the products are going to be favored. And the reaction is likely to shift left. Because Q is greater than K. In this case, Q was less than K. And in the second instant, Q, highlighter. Q is going to be greater than K. Okay, so now we have delta G, Q, and K, all of which help us predict reactions direction. Okay. So this wants you to, it says, because delta G is the distance in free energy from the equilibrium state for a given reaction shown below, delta G is 0 at equilibrium, so point number 3. With this knowledge, convert the previous equation into one that relates delta G naught and K. So starting off, so we know that at equilibrium, the following is true. Q equals K, and delta G for current conditions must equal 0. Therefore, if we go back to that equation that we started with, and we start plugging in the assumptions we make at equilibrium, and then we start rearranging, and we want to convert between, so that K and Q are related. K and delta G are related. We see that this is the relationship between delta G naught and the equilibrium constants. Okay, so these are just algebraically rearranged. I'm not going to expect you to be able to convert, but you need to know these equations. Okay, so you have 2 there, 1 right there, and where's the other one? A 4th one right there. Okay. All right, so let's look at the problem. This says, so let's, real-time editing. Calculate the KEQ from the previous problem. Compare Q to KEQ for each set of conditions. Verify that the results of comparing Q to KEQ match the results of comparing delta G to 0. Okay, so let's see, we have K, E to the delta G naught of the reaction divided by R times T. So in this case, I'm going to plug in E to the negative 13.6 times 10 to the, or times 1,000, because I need it to be in kilojoules. I need it to be in joules, and it was in kilojoules. And the temperature is 298 Kelvin because it doesn't specifically tell us that, but we're going to assume STP, so 298 Kelvin. This value comes out to be 0.00413. So in this case, we calculated Q to be 0.001 and K to be 0.00413. We see that indeed Q is less than K, and it would shift to the right. And if we go back up and look, we predicted the reaction would shift to the right. If now we want to calculate delta G, want to know what delta G is. My delta G of the reaction is going to be the same as the top part up here, plus R 8.3145 joules per mole Kelvin times the 298 Kelvin times the natural log of the quotient, which I calculated to be 0.001 in one case and 1,000 in the other. And so the delta G for the first scenario comes out to be negative 30.7 kilojoules per mole. If I do the same for the one that was Q is equal to 1,000, I'm going to get that delta G is equal to 3.52. And this should be joules. Joules per mole, indicating that it's non-spontaneous in the forward direction. Which, if we go back and we look at the two situations, with the first one we said that the reaction is going to shift to the right to produce more products, making it spontaneous. In this case, in the second one, when Q is greater than 1,000, we said the reaction is going to shift to the left, and that it's going to be non-spontaneous in the forward direction. It'll be spontaneous in the reverse direction. Okay? So this can help us predict spontaneous in which direction. Q and K help us predict shifting left and right. Okay. So we are not going to worry about thermodynamics of living systems. Okay. It's pretty interesting stuff. ADP, ATP. If you're a biology major, you will learn all about this in biochemistry and I think genetics and cell bio. You'll learn about it a lot. If you are a chemistry major, you probably do not care much about ATP. What you learn in gen bio would be sufficient. Okay, so let's do a brief recap. So we have enthalpy, delta H, less than 0, negative, exothermic, greater than 0, positive, endothermic. Entropy, delta S, greater than 0, spontaneous, equal to 0, at equilibrium, less than 0, non-spontaneous. Typically, our reactions tend to be favorable when they are exothermic and entropy is greater than 0. We cannot necessarily determine them individually because they both have a determining factor in spontaneity. So we use what's called Gibbs free energy, which is G, to determine its spontaneous, which one, forward or reverse. That brings us to an equation, which is delta G equals to delta enthalpy minus the temperature times the change in entropy. If the delta G is less than 0, it's spontaneous in the forward. If it's equal to 0, then it's at equilibrium. Q equals K. If the delta G is greater than 0, positive, it's non-spontaneous in the forward direction, but it's spontaneous in the reverse direction. We have this table, which helps it. Okay. This table here, which will help us to predict what the sign of delta G may be. You need to know that table. Then we practice predicting the sign based on It's given us exothermic. We know how to determine entropy because we can look at the phases or the number of moles. We did that in a couple of problems before and predict the sign of delta G. Then we calculated the delta G using our delta G equals enthalpy minus temperature times entropy. This should be a delta S. Okay. We just plug the values in, making sure they're in the same units. The reason why we used delta G equals 0 is because that's the last point at which the reaction goes from being spontaneous to not spontaneous. So setting that as the bar, we're crossing over the line one way or the other. And so 0 is like, it's like having a pH of neutral. It's only 7.00. The reaction is only at equilibrium at 0.00000. So when we go at one side of the temperature, or either side of it, we are going to be switching from spontaneous to not spontaneous. Then we used the individual Gibbs values, just like we did enthalpy and entropy, to calculate the Gibbs free energy of the equation. And this is assuming at 25 degrees Celsius. They're in the appendix. No, you don't need to memorize them, and they work the exact same way the entropy values did. We skipped phase changes, and then we ended up with relating free energy and equilibrium. So we already know that when Q is equal to K, this is at equilibrium. Products and reactants may be forming, but they're happening at equal rates so that there's no net change. And then we're going to relate that to free energy using this equation right here in the upper left-hand corner, taking the non-equilibrium delta G with the equilibrium delta G and the reaction quotient. So it's going to tell us how far off of equilibrium we are. And remember, R is 8.3145 joules per mole times Kelvin, and temperature must be in Kelvin. So then we calculated Q for both reactions, and we saw that when the first scenario, Q was much less than 1, suggesting that we were pretty far from equilibrium, and the reaction was going to be shifting to the right to produce products to bring us closer to equilibrium. The delta G of the reaction, which are values from the table, confirmed it because the delta G is negative, meaning it's going to be spontaneous in the forward direction. When we looked at Q in the second set, our Q was great. It was 1,000, so it was much greater than the previous scenario. It's also greater than K when K is equal to 1, so it's going to suggest that there are too many products around, and the reaction is now going to shift back to the left to bring the equation back to balance, because the delta G of reaction is still negative, suggesting that while products are favored, it's going to shift back to the left because there needs to be a balance between the reactants and products. Then we took what we know about equilibrium, plugged it into the equation that we started with, and said, okay, how can we relate delta G naught to K, which are two equilibrium constants? So we set Q and K equal to each other, delta G equal to 0. We plugged those values in, we rearranged it, and we got the two formulas here. Okay, and so these are two more formulas to note. Then on the very last problem, we took what we did before, and we saw that when we solved for K, the actual equilibrium constant for this equation is 0.00413. And we saw that when Q was 0.001, that the reaction was going to shift to the right. And that when Q was 1,000, it was much greater than K, and it was going to shift to the left. We calculated the delta G values to see, does it agree with the spontaneous in the forward or reverse? And we see that for the first set of conditions, when the reaction is shifting to the right, that's in the spontaneous direction. And then when we have a Q value of 1,000, it's no longer spontaneous to proceed in the forward direction. It's now going to be spontaneous in the reverse direction. So the reaction is going to reverse itself, produce more reactants, which they all just agree with each other. It's kind of like when we did acid and base classification. We said, you know, if it's an acid in one set of definition, it's an acid in all of the definitions. We're just changing how we're classifying them based on the information we have. And that's kind of how this is. We're not changing whether or not something's going left or right, or whether it's spontaneous or not. We're establishing it using different sets of parameters. So we're not looking at just enthalpy and saying exothermic means spontaneous, and we're not looking at just entropy and saying greater than 0 means spontaneous, or Gibbs and saying less than 0 is spontaneous. We're taking all of them together and saying they all show the same thing and they all agree with each other. And so it's important that you realize we're not classifying these in any other way besides just with the information that we have. So you'll have to look at the information you have in the problem and decide which formula best fits the information you're given and use that formula. Okay, so this ends all of chapter 16. I really recommend making note cards, knowing these formulas pretty well. And the next chapter starts off with electrochemistry. And so the lab that we'll be doing this week should match up with the lectures because it's electrochemical cells. And then hopefully if you have any questions, hang on to them and we'll do the session at the end of the week and go over any questions.